Imagine a future where holding the high ground does not mean holding the next mountain or holding air superiority. Imagine a future where holding the high ground means having space superiority, right? What we do at Atmos is we develop technology to return any type of cargo from space down to Earth, and that can be in a lot of very diverse markets, from in-space manufacturing, experiments, space agencies, returning complete rocket stages, all the way to defense.
5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
Hey, space enthusiasts. Welcome back to another episode of the Space Business Podcast. My guest today is Sebastian Klaus, and he is the co-founder and CEO of Atmos Space Cargo. Welcome, Sebastian.
Thanks for having me.
Sebastian, the way we usually start this off is with an elevator pitch by the entrepreneur. So do you mind?
I do not mind at all. Yeah, thanks for having me. I'm Sebastian. I'm the CEO of Atmos Space Cargo. We are a European company founded by 4 co-founders, Marta, Jeff, Chris, and me. The 3 of them come from the space industry. We can talk about that in more detail. I come from a defense and space background. And what we do at Atmos is we develop technology to return any type of cargo from space down to Earth. And that can be in a lot of very diverse markets, from in-space manufacturing, experiments, space agencies, returning complete rocket stages, all the way to defense. And yeah, the company is now 3.5 years old. We are around 50 employees. We've raised more than 10 million euros in venture capital. And we have just conducted our first mission to space and back.
That's great. And we will definitely talk about that most recent news on the very recent mission. But so taking a step back and fleshing out some of the points you mentioned there. So can you walk us through what you see as the main use cases of having the capability of coming back from space? I think many of the listeners are obviously very familiar with the use case of going to space and taking something there and putting something there, like principally satellite. But why do you want to come back from space? What are the main markets there?
Yeah, that's actually a really good question. I always thought that I think the main reason why there's not more happening in space is just because it's too expensive, right? And it's actually not that expensive because it's so complicated, like technically. I mean, when you look at what's happening in quantum or in AI, these things are way more complex than, let's say, the engines in a rocket, right? Like they work the same way they've been working for 80 years pretty much. But I think the main reason it's so expensive is because everything that we build for space is just used a single time, right? So you shoot it up to space, be it a satellite, a rocket, or an experiment, and it just burns up on reentry, right? So if you are able to bring things back from space and you can reuse them, that changes the whole economics. And SpaceX has shown to everybody how that works with the Falcon 9 and now with the Starship in the future. And so I think it becomes very clear that this problem of returning things from space is really super important for the whole industry. And that's why we said, let's try and solve that and solve it in a way where we can return anything from space.
Yeah, but you also make it sound like, forgive me, a little bit simple, right? You're always like downplaying the rocket science there, which is kind of funny, right? Because we usually have this, way of saying like, hey, this like it's not rocket science, right? And you were kind of almost implying we should change that saying to sort of like, hey, that's not like AI or something. But I think when we talk about downmass, I mean, it is noticeable, right, that if we talk about sort of bringing the most precious thing back from space, arguably that would be astronaut lives, right? Like they really should come back when we send them up there. But it's only like very few nation states who have this capability to date, right? And I think that's probably for a reason, that it's expensive and not that easy. Do you want to talk us a little bit through that, what the maybe additional complexities are to bring something back from space versus just bringing something up from Earth?
Yeah, absolutely. I mean, the first thing that we need to differentiate between is orbital flights and suborbital flights, right? So I think everybody has seen Katy Perry going to space on the Blue Origin New Glenn a couple of days ago. And, if you just fly straight up to space to 100 kilometers and then just drop down, that's fairly simple, right? Fairly simple, I want to say. But the real complexity comes in when you're flying orbital, because when you're flying orbital, you're not just going straight up and down. you're actually going in circles around the Earth and you're going super fast, right? Like we're talking 8,000 meters per second, roughly 25 times the speed of sound. And you have so much kinetic energy in your moving vehicle that if you were to just convert that kinetic energy into heat, like, like you do in a brake of a car pretty much, your whole vehicle would just vaporize, right? So it would just disappear from the heat. And so you need to find a way to get rid of all of the heat. And there's pretty much three different ways of how you can do that. And the first one, you have just mentioned that there's only very few nations that can actually bring back astronauts from space. And the technology that is still being used for this today is what's called ablative heat shields. And when you use an ablative heat shield, what you're doing pretty much is you go into the atmosphere with a flat surface heat shield, and this heat shield burns away during the reentry. And by burning away, it cools the rest of the vehicle, right? And this is a very reliable technology. It's actually been developed already in the 50s and 60s of the last century, first for nuclear warheads and then for astronauts. And it's still being used when high reliability is of the essence, right? Like SpaceX Dragon, for example, or the Russian Soyuz. But by definition, it's not reusable because it burns away. And it's also kind of not very efficient in terms of mass and also in terms of the volume. Like the things that you want to bring back from space, they need to be shaped in a special way, right? Like all of those capsules, they look like little cones. So NASA tried to come up with new ways of solving this problem. And I think everybody has seen the space shuttle and probably also the SpaceX Starship. And what these vehicles use is what's called heat shield tiles. So they are ceramic tiles that can be reused, but they are also kind of brittle. So the space shuttle was always losing tiles. We see the same now on the SpaceX Starship, even though it's like, 40 years later, it's still the same kind of problem, shedding tiles. And so NASA tried to come up with an even more innovative solution in the late 90s and early 2000s. And that solution is called an inflatable heat shield. And that's what we also do. And that's the innovative part here.
Okay, and without going into the deep part of the technology, since we're billing ourselves as a non-technical podcast, how does if you're talking about inflatable materials that at least people like me sort of intuitively think, well, that sounds like something like plastic or so that's going to burn even easier. Like, how do you deal with the heat management on those
that's a very
inflatable
good question.
materials?
Yeah, so the key here is what's called the ballistic coefficient, and I'll try to say it as it's in a very non-technical way. I think everybody has seen a skydiver, right? So when you have a skydiver, that skydiver is maybe like 80 or 100 kilograms. And when that skydiver jumps from the plane, he can reach a speed of around 200 kilometers an hour, right? And then as soon as the skydiver pops the chute, the surface area of that falling object becomes much bigger. And we call that a decrease in the ballistic coefficient. So you have the same mass, but more area to slow it down. And that reduces the vertical velocity of the skydiver from 200 kilometers an hour to maybe like 10 or 20 kilometers per hour. So same principle here. So what we do is we increase the area of the heat shield by inflating something. And that makes sure that we can already decelerate very far up in the atmosphere. And when you decelerate further up in the atmosphere, you actually reduce the amount of heating, like the maximum heat flux, and also the amount of deceleration that you have. As you can imagine, like the thin layers of the atmosphere, they just exert less force and less heat on your vehicle. So we still get hot, but by far not as hot as these ablative capsules, right? Like whereas the Soyuz has more than 2000 degrees Celsius on the outside, we have roughly 1,100 degrees Celsius. And at that point, you can use some fairly normal materials like ceramic fabrics, for example, that we use for these inflatable heat shields to slow yourself down.
Gotcha. And so you mentioned before that NASA looked at this, I think you said in the late 90s. Is there any specific reason why? I mean, because this all sounds great, including the last part you mentioned there. It seems like it's also like a softer re-entry or softer deceleration profile, which has to be, I assume, good, like both for humans, but also for like certain types of materials you're bringing back. So it sounds like it's all advantages, like potentially lower cost because it's more reusable, softer re-entry profile. Was there any specific reason why NASA didn't pursue this any further?
Actually, NASA did. This is really like the latest technology that NASA has also developed. So we are not building this completely by ourselves, right? So 10 years ago, there was a very successful program from NASA called the HIAT, the Hypersonic Inflatable Atmospheric Decelerator. And then just 2.5 years ago, there was a flight called LOFTID, the low Earth orbit flight test of an inflatable decelerator. And I mean, like 2.5 years ago in NASA terms, that's yesterday, right? So,
Sure.
so what NASA is doing there is, for example, they are working together with the ULA, the United Launch Alliance, and they are trying to commercialize this technology to bring back the engines of the United Launch Alliance's newest rocket. And the technology is also being used by one of our competitors in the US, a company called Outpost. So they also work on these types of inflatable heat shields. So yeah, it's really the latest state of the art in this type of technology. And in Europe, we are the first commercial company to try and bring this into the market. There is one European state-funded program that is also working on inflatable heat shield. It's called Ifesto Icarus. It's led by Deimos, and we are also part of that consortium. And this is, let's say, a little bit more of a conservative approach. So very, very similar to approach to what NASA has been doing before. So we work also on that, but then we also have like our little, our little secret sauce in our system that we develop.
Gotcha. And so since, Atmos is a commercial company and not a space agency or a government program, let's talk a little bit about sort of the economic impact of that. So I assume because it's more reusable than the historical materials, there's going to be some cost advantage, or at least you guys hope to achieve some cost advantage by using this technology.
Yeah, exactly. So let me give you a concrete example. I mean, I'm a fan of your podcast, right? Like I've been listening to you for years already. And so I also heard some of the episodes where you were talking about Varda, for example. And when we compare our approach to what Varda is doing, there's advantages and disadvantages, right? Like, so what Varda has been doing worked at the first try. So you got to give them credit for that. They used some very, reliable components like the photon kick stage from Rocket Lab and like a classic ablative capsule. And so they already brought back 2 capsules from space successfully. And that's, I think, very important for the industry as a whole to show that this can be done by private enterprises and that there's a market for that. So yeah, we owe them a debt of gratitude for that. However, what they do is pretty much they throw away their satellite bus every single time that they go to space, right? So the propulsion system, the solar panel, the communication, all those things that are expensive, they are thrown away. And in our approach, because we have this inflatable heat shield, which allows us to bring back large mass and also very oddly shaped objects, like, for example, spacecraft with thrusters and antennas and cylindrical objects that don't fit into the classic cone shape, we can actually bring back everything and then reuse it, right? So it's not so much actually about the reusability of the heat shield, but more about the reusability of the whole spacecraft. That makes a huge economic difference.
Gotcha. And so you're actually bringing up a good point there, talking about the spacecraft and mentioning that it's not only about the heat shield, because I do realize now we spent actually quite a bit of time talking about specifically the heat shield, but thermal protection systems are sort of a very interesting topic to talk about and very relevant here. But yeah, let's talk a little bit about the broader tech stack, right? Because like everything you need. So obviously your spacecraft, it is a spacecraft, I guess, like has to go up on some vehicle, right? So I think you're currently going up on SpaceX, right? Then what happens? I guess you have to get to a certain target orbit, right? Then I guess at some point in time, you have to leave that target orbit and go into a certain desired reentry profile. So you're kind of coming back where you want to come back. And then you have to, and then we have to explain the coming back as well. Like, how does that look? Is there like, for example, parachutes? Do you like Varda lands on land? Do you guys land on water? If it's on water, how do you find your capsule? Can you talk us through the broader tech stack?
Yeah, of course. So first things first, you have to select a launcher, right? Like we're not a launch company, even though, with Icarus, for example, we are also working on the technology that can make launchers reusable. We are really very much focused on the downmass part. So first thing we do is we select a launcher. This could be SpaceX, like we have done now 2 weeks ago on our first test flight, but it could be also any other type of launcher. So we have a standardized interface It's called a 24-inch ESPA ring. That's a standard thing that is flown by SpaceX, but also by, Rocket Lab and ESA Aerospace and Rocket Factory Augsburg, Latitude, like all of those companies, they have the same types of interfaces. And so once you have selected the launcher, you have to select your orbit. And in most cases, we can work with pretty much any orbit. So we go more for the affordable, the rideshare missions, like, for example, SpaceX Transporter or Bandwagon. So we don't really care so much about the orbit. The only thing that is important for us is we want to go to low Earth orbit. So typically between, let's say, 400 kilometers lower limit, 800 kilometers upper limit. And then we want to have an inclination that is at least big enough to bring us to our favorite landing sites, right? So if the inclination would be 0, like flying over the equator, well, then we could only come back over the equator. And obviously we want to come back to Europe or to American landing sites as well. So then once the launcher has deployed us into orbit, first thing that we need to do is switch on the spacecraft and get some telemetry down, right? So we need to use ground stations, or we need to use inter-satellite links like, Starlink or Iridium or OneWeb. And then we establish a connection to our spacecraft in space. And inside of that spacecraft, the customer payloads begin their work, right? So it could be a bio payload, it could be an in-space manufacturing payload. And we make sure that our customers have connection through the payload so that they can, activate an experiment, download some data, stop or start a new process. And while the customer does that, we also have to do the health keeping on our satellite, right? So we have to make sure that we get the right amount of power, that we are, in the right thermal state. And then at some point when we want to come back from space, this could be after like 2 or 4 weeks, we have to actually fire our engines to come back from space. So it's called a deorbit burn. So we slow down our spacecraft by roughly 150 meters per second delta V. And that slows down the spacecraft just so much that the perigee of your orbit is inside the atmosphere. And then the atmosphere does the rest of the braking for you. And so before we go into the atmosphere, we deploy our inflatable heat shield, and then the atmosphere slows us down. And while we are in the atmosphere, we can actually also steer, and that's an important thing to mention here. We have what is called a lifting reentry, and a lifting reentry means that you generate not just drag in the atmosphere, but also a tiny amount of lift, and you can use that lift to keep yourself in the upper layers of the atmosphere for longer, just like the space shuttle did, for example. And that further reduces your G loads and your heating. And it also allows you to steer precisely to where you want to land. So for example, on the next flight mission that we're going to do next year in summer, we want to land in the Azores, Portugal, so in the Atlantic Ocean, to be able to recover that vehicle and then bring it back to Europe. And then once we have landed the vehicle, so we typically land in the ocean, then we take it out of the ocean and we bring it back to the customer, where we take the spacecraft apart, return the payloads to the customer, and refurbish the vehicle for the next space flight. Because what we're talking about here is a fleet of reusable vehicles, pretty much just like SpaceX is operating the Falcon 9 to go to space in rideshare missions. We want to offer the same to come back from space down to Earth. So yeah, in a nutshell, that's the whole cycle.
That's great. There's a couple of follow-up questions on that. So one starting with the reusability, right, which is so interesting economically here. Like, what is the gating factor here to ultimately, if we dream of a future where downmass becomes very frequent, very high cadence, and there's maybe a lot of in-space manufacturing going on, sort of, how often do you guys would like to fly, and what is the gating factor of that? For example, is that going to be launch cadence? How often you can go up? Is it going to be sort of a refurbishment period? Is it going to be the number or the clip at which you are able to produce these capsules, even though they're reusable in-house? Or how do you think about that?
So our plan currently calls for 2 flights next year. And then the year after, we want to go to a quarterly launch cadence, so roughly 4 flights. And then the year after, we want to go slowly towards monthly flights. So we think that is something that is very realistic and achievable, because we see it also with other companies in the market, right? Like, I mean, SpaceX is now launching hundreds of times every year. So there's enough launch opportunities. And we also see with Varda that they have been flying twice in a very short time frame. So there's no showstopper there in terms of the cadence. I think what we want to see in the very long-term future is that you can pretty much go to space more or less on a daily basis, like on a regular schedule, where there are vehicles going up and down, and you can just book your flights even last minute, right? Like on a plane. We're not there yet, right? Like currently, it's a huge process to get a payload on such a vehicle and to qualify it for the flight. You know, all of the vibration testing and vacuum testing and documentation required to be allowed to fly to space. But once we've proven that, you know, the vehicle is safe and it's like a fleet that does recurring operation and the payload is safe inside of it, no matter what happens with the payload, I think there's nothing that's stopping us from pretty much like daily access to space. I think that's where we want to go.
Gotcha. But since you mentioned the word showstoppers there and bottlenecks, and you brought up VADA, I mean, VADA had this situation where they were actually stuck in orbit for a while because they couldn't get their re-entry license to land on the continental US. Do you consider that like a solved problem now coming back to Earth from a regulatory point of view?
I mean, I didn't want to bore the listeners with the regulatory aspects, but I mean,
we can spend 2 minutes on it. Not more.
Yeah, it's something that you have to take very seriously. Yeah, I mean, we've seen it with Varda that they were pretty much stuck in space for half a year. And so, yeah, we saw that and we learned our lesson. So we started very early to work with the Federal Aviation Administration to make sure that we had all of our licenses in place for this reentry. And we also made the conscious decision that we would do our reentry over open water, right? Like, because in the end, it's a question of risk always. And if you're re-entering close to population, close to airplanes, close to people on the ground, then your risk is just higher. If you are landing pretty much in the middle of nowhere in the Atlantic Ocean, then the risk is lower and it's easier to get the regulatory aspects done. So yeah, we had to get what's called a payload determination from the Federal Aviation Administration. We also had to get a waiver from the German Space Agency, DLR. We had to get our frequency rights from the ITU, of course. And so all of this has to be done in parallel to conducting such a mission. But there again, like once you are doing operations that are recurring, you're doing the same type of process over and over again, it gets easier, right? So there are such things as, for example, in Portugal, where we want to come back, they have what's called a global license. So once you have that license, you can use it over and over again for your reentries. And that's, of course, what we're aiming for. And we're also doing some things that are already going in that direction. So, for example, Phoenix is using what's called an ADS-B transponder. So it's a transponder that you typically find in aviation and in drones. And you can probably already guess why we are going for that, because we want to operate this vehicle pretty much like an aircraft or like a drone, so that it blends into the airspace with other aircraft, so that it's not always, you know, closing the whole airspace, but rather flying through it.
Makes sense. And I just realized I should have asked earlier, but I haven't asked you about sort of actually the size of this, right? So just for our listeners, is this like a container size thing dropping on your head or something smaller? Like what's roughly the size and mass?
Well, it's actually quite substantial already at the first flight, right? So the first flight that we did, it was a 250 kilogram spacecraft. So in packed state with like the heat shield compressed, it was already 1.5 meter diameter. So the size of 2 dishwashers pretty much. And so this vehicle has like around 100 kilogram of payload capacity, right? So you can already carry things like these ISS mid-deck lockers that you find on the International Space Station. You can carry smaller CubeSat-sized payloads, but 100 kilogram already allows you to do a lot. And this is only our first demonstrator, right? It was really just a test flight. We see the technical limits of these inflatable heat shields at roughly 25 metric tons. So, I mean, yes, you were joking about a shipping container, but that's exactly what we're looking at, right? Like it's a 20-foot shipping container that we could bring back from space.
Gotcha. Okay, and so last question, sort of on what I'd call the tech stack. So right now you're going up on SpaceX Falcon 9. How do you see Starship changing or not changing what you guys are doing?
I think we're all looking very much forward to Starship becoming operational, because I think what's going to happen is that the cost per kilogram, which currently on a rideshare mission is roughly $7,000 per kilogram, will continue to drop. I think at least an order of magnitude. I think we might see prices below $1,000 per kilogram on Starship. And that changes a lot also for our customers, because currently the launch cost is still one of the main contributing factors for all of our missions. So if the launch cost goes down, we can also offer lower price per kilogram. Well, the question is, of course, is Starship a competitor for you? I think in some areas it will be, right? Like if we're talking about mass manufacturing of large amounts of materials in space, where you don't really care about, how long they stay in space and when they are being taken down. It's only really about price per kilogram. Yeah, then it is some sort of competition. But for most of our use cases, it's actually not, because, I mean, you know this very well because you are very deep into, for example, biomedicine in space. If it's about, staying in space for like 2 to 4 weeks, like exactly what you need for your experiment or for your biomedical development in space, then Starship is probably not the best option, right? Like, because the bus will not wait for you, right?
Yeah, it brings up an interesting broader question as well. So, if somebody came to you and said, Sebastian, I want to do something in space, I know some sort of in space manufacturing. There's all of these platforms now. There's like VADA, there's you guys, there's some others. And then we haven't talked about this yet, there's the space stations as well, right?
Yeah.
Like these proposed replacements of the ISS. And so if somebody came to us like, Sebastian, should I use the space station or should I use you guys? I mean, I have my view on the answer, of course, but how would you answer that?
I would say it depends. And in most cases, you can actually do both. So, if you want to have a good price and if you want to be very flexible in terms of your time, like how long you want to stay in space, I think free flyers are the better option, right? So we can offer you something that is price-wise very competitive in comparison to the real commercial prices on the International Space Station, for example, subsidies taken out. And I mean, you talked about it, I think, in one of your last episodes also. Cost for an astronaut is like 130,000 per hour. Like for that price, I can shoot 3 kilograms to space and back again, full end-to-end mission. I mean, you can choose between having that astronaut for 1 hour or sending a university payload to space and back again, all included. So I think it's very, very competitive. And the other thing is that we are actually in talks with some of those commercial space station providers to offer an alternative return solution, right? Because these space stations, they will have some sort of a bus coming for them, right? Like let's say a SpaceX Dragon or exploration company Nix, or one of those large vehicles. But this vehicle will not go there on a daily basis, right? Like it will go there maybe like once every 3 to 6 months or something like that. But if you need to have your biological experiment, your living cells down after like 2 weeks in orbit, you might want to have a different vehicle to bring it back down. And that's something that we're also looking at in the midterm future, to have like a small vehicle that could bring things down from space stations on demand, right? It's very comparable in terms of the technology to what we do on Phoenix 2 anyway. So yeah, we're looking at that too.
Good stuff. Okay, so this is a nice segue, kind of shifting from talking about the tech stack to talking about the markets and the use cases. What do you see as the main use cases? What do you see as your first use cases? Who actually are your customers?
Yeah. So the important thing to understand is that we are a logistics company for space, right? So we are not the ones that do in-space manufacturing or experiments. There are other companies out there that are vertically integrated in that area, like Varda, for example, but we do not do that. We focus on logistics. And that means that we have pretty much 5 different market segments that we go for. So I think the most important one for us right now is biomedicine in space. And of course, we are not doing this alone. We are doing this with partners, like implementation partners. We sometimes call them brokers, companies like URI or Space Pharma, Redwire, like all of those companies that already have experience in conducting biomedical R&D in space, primarily on the International Space Station. And we work with them to bring these types of experiments to space. And it's really super interesting things that are happening there, right? Like, I mean, we're talking about organoid production in space. We're talking about 3D printing of human tissue. I mean, think about the possibility of actually creating 3D printed organs in space, right? Like it could be completely life-changing for people. There's cancer research happening in space. There's aging research happening in space. So it's really things that people on the ground can actually benefit from, right? And that's one of our most active market segments. Actually, on the first test flight, we already had 2 biomedical customers on board. And then the second market segment that I think is also, very interesting for you, we've been talking about it a lot in the last couple of episodes, is in-space manufacturing, for example, for things like semiconductors or glass fiber, Zibelan glass fiber. Yeah, so these companies, they benefit from the unique properties of space, like the extremely clean and high vacuum in space, but also the weightlessness in space to produce, for example, better crystals in thin films and better crystals in glass fiber. And then the third market segment for us is all of the space agencies that do their microgravity research in space. And I think, as pretty much most of your listeners will also know, the International Space Station is nearing the end of its life, and it might actually be deorbited even earlier than what was initially anticipated. Because, yeah, I mean, we've all seen the big proposed budget cuts to NASA, and we've also seen that Elon Musk is pretty much advocating for an earlier end to the ISS to go to Mars instead. And that means that a lot of the research that is being done by space agencies on the International Space Station will need new destinations. And there's not a lot of alternatives to the ISS right now. I mean, nobody's flying with the Chinese for obvious reasons. And also nobody's flying with the Russians anymore. So that leaves pretty much America and Europe as the only options. And yeah, we are one of the few companies that can offer you right now to fly on one of our vehicles to space. Then what we also do is defense applications, and this can go all the way from military logistics through and from space to in-orbit demonstration for military payloads. I mean, think of the American X-37B, right? Like the little vehicle that can go to space and demonstrate, for example, military antennas or reconnaissance payloads in space and then bring them back from space. Well, we can do the same. We don't have wings, but the principle is exactly the same. Well, if you think a little bit more futuristic, if you think, let's say, 5 to 10 years into the future, if you're thinking about things like sample return from the moon or from Mars, if you are thinking about mining asteroids, if you're thinking about mining helium-3 on the moon, like all of this material needs to have a way of coming back from space. And what we are trying to develop here as a logistics company for space is an end-to-end service to get your material from space down to Earth, whatever the material is.
Yeah. And so just picking up one of the things you highlighted there, also given your, like you mentioned at the beginning, you do have a defense military background, right? So these defense applications, because it's interesting, if you looked at some of the US companies you mentioned, like Vada and Outpost, I mean, they basically all have reasonably sizable contracts from the US Department of Defense to be used for their vehicles to be used for hypersonics testing. Is that something you see happening in Europe as well? And if not, is it something that maybe should be happening in Europe?
That's a very good question. So I have been serving indeed for quite a long time. I was 14 years in the German army as an officer, and I saw the state of the German military. And unfortunately, I have to say it's really not in a very good state. After, pretty much 80 years of peace in Europe, we thought that we wouldn't really need the military anymore, right? So the only things that we did was, I did 2 deployments to Afghanistan, for example, and that's where we were still spending some money, but we were not really spending any more on defense against big adversaries like Russia, right? And this has only changed really since early 2022 when Russia invaded Ukraine. Since then, there has been a massive increase in spending, especially in Germany, but also in the rest of Europe. And so if you had asked me like 5 years ago, I would have said like very clearly the only country in the world where you can do something like military logistics through space would be America. But if you ask me now, I would actually say that the market opportunity for us in Germany and in France and all of the other European countries is actually bigger than the market opportunity that we would have in the United States. So yes, we're going for it actively. Maybe I can say just a few words about that as well. So, I did study aerospace engineering in the military, but I was also deployed as an officer, first in the infantry and then in special operations to Afghanistan and to Africa. And I was using also fire support there, for example, from drones and helicopters and airplanes. And imagine a future where holding the high ground does not mean, holding the next mountain or holding, air superiority. Imagine a future where holding the high ground means having space superiority, right? Like if you can have effect from space down onto the battlefield on the land or in the sea or in the air that makes all the difference. And when you combine that thought with what's happening, for example, in Ukraine right now, with all of the drones and the artificial intelligence that is being applied there, I think you see where I'm going, right? Like, I think the battlefield of the future is going to be also fought in from space using drones, using artificial intelligence. And we are actively working on such programs.
Yeah, and maybe just, because I don't want to dwell too long on it, but maybe like the last element, you mentioned somewhere there in the middle, also the logistics element of, so I mentioned hypersonics testing, but even before that, you mentioned also the potential to, well, that logistical element, right? Because I mean, you could have this idea, which is, I think, already publicly known in the US, that you could have depots in space and then rapidly deploy basically to any place on Earth. And you tell me, like, actually, maybe for our listeners, what rapid actually means, whether that's like 30 minutes, a few hours, or so forth. But I mean, that seems very fascinating, right? And you're much more of a military expert than me. But I remember that I think there was some US general, like in the Second World War, who said something like, infantry wins battles, but logistics wins wars, right? So that seems, quite relevant.
100% accurate. 100% accurate, Rafael. That's exactly it, right? So people are always fascinated with, let's say, like the latest weapon systems, but when you look at what's actually happening in wars between peers, like pretty much big countries that are equal, in the end, the better logistics wins, the better industrial potential wins. And so having depots in space is actually something that is very realistic, right? Like, I mean, imagine a constellation of satellites that is in polar orbits. So that means that your satellites are circling over the North Pole and South Pole of the Earth every 90 minutes. And then the Earth is circling under that. So if you have a little constellation of, let's say, maybe like a dozen satellites in different orbital planes, so with different angles, that means that you can pretty much reach any place on Earth within, let's say, 60 to 90 minutes. And I mean like any place on Earth. And you can also come from directions that are very hard to predict and foresee, right? So, for example, when you think about very big countries like Russia or China, they typically defend their borders with their air defense. Now imagine you do a reentry in the middle of the country. Right? So it has huge military potential, and especially in areas where huge distances are involved, which means, for example, Russia, but also in the Indo-Pacific, right? Like, I mean, we're talking 10,000 to 15,000 kilometers from the US West Coast to Taiwan, to China. When you have these vast distances involved, coming from space within like 60 to 90 minutes makes all the difference.
Gotcha. That's fascinating to think about. Okay, let's change tack a little bit again. Where are you guys right now? What are the next steps? I mean, I guess the first thing to talk about is your recent test flight.
Yeah, so we have indeed quite a test program going on, because this technology that we are developing, the air-breathing inflatable atmospheric decelerator, is technologically very advanced. So it requires several test flights, right? Like, you can pretty much compare it to what SpaceX is doing with the Starship. And we have just done our very first orbital test flight just 2 weeks ago. And so we went to low Earth orbit. We lifted off from Kennedy Space Center in Florida on a Falcon 9 rideshare mission called Bandwagon 3. So we went to a roughly 500 kilometers altitude orbit, 45-degree inclination, and then we went around the Earth once. And then once around, SpaceX did a deorbit burn for us. So they slowed down the vehicle and then deployed us into space. And the good thing is that our vehicle, immediately after deployment, it switched on. Right? So it was a huge relief, I can tell you, because I think every satellite builder's worst nightmare is that, you build your satellite, it takes you years, you test it, and then you send it to space and it just stays silent and you have no idea what's happening, right? So luckily for us, the vehicle switched on immediately and we immediately got telemetry data. So we used UHF with ground stations along the flight paths all the way from Los Angeles over Central America, Brazil, and then down into the South Atlantic. And we got a lot of flight data. We also had customer payloads on board and also got some customer data down, which is also very important, because that means that from now on every flight that we do to space, we will have paying customers, right? Like, we will make money on every single flight that we do now. Yeah, we operated this mission pretty much on 3 continents. So mission control was in Lichtenau. This is our headquarter in Germany, just on the border to France, where we also have an office in Strasbourg. Then we had launch in America, and we had the re-entry off the coast of Brazil. So we were working in parallel with 3 teams, and that also worked very well. And yeah, all of that data that we got now from this first test flight is what informs the development of the next vehicle now. So next vehicle we call Phoenix 2, and we're going to fly it next year. And Phoenix 2 is going to be much more capable already than Phoenix 1. So it also has around 100 kilograms of payload capacity, but it features its own propulsion system. So we can stay in orbit, let's say 2 to 4 weeks probably on the next mission. And then we will fire our own thrusters to come back from space and attempt a re-entry to the Azores, Portugal. We're going to have solar power on board to generate roughly 100 watts of power for the payload. And yeah, on this vehicle, as I said before, it's launch agnostic, right? So it might happen that we're flying on SpaceX again. It might also happen that we fly on a different vehicle, but that we will see next year.
Okay, terrific. And then we already touched upon your sort of long-term vision, which is like going towards monthly and maybe even daily flights and so forth. Do you see any sort of, I mean, we touched a little bit on bottlenecks, but if you look at this long-term vision, is there anything on your mind that we still need to resolve to make this future happen?
Yeah, so I think, in the long term, there are going to be customers who really still care about the duration of staying in space and also the location of coming back, right? So if you come back on a SpaceX Starship, you will come back in Boca Chica, Texas, right? Or on some offshore landing platform. You're never going to come back like close to population in Europe or in America, right? Like, because that vehicle is massive, it's very loud, it's dangerous when it comes back. So I think there's always going to be some customers that really want to decide exactly how long they stay in space and where they want to come down. And that's something that we can cover with our Phoenix 2 vehicle. But then in the long term, there's also going to be customers that really only care about the price per kilogram. And that means that we have to take economies of scale into account. And so what we already have on our roadmap is a larger vehicle we call Phoenix 3. It's going to have roughly 10 times the payload capacity, and that's going to bring down the price per kilogram, right? So our current price per kilogram is roughly 45,000 euros. So meaning that for the price of a car, you can pretty much send a university payload to space and back again with us. And in the long run, I think it's definitely possible to bring that price down at least by half, if not down to a third or something like that. So that's what we're aiming for with our larger vehicle, Phoenix 3, for scaling.
Okay, terrific. Okay, we're coming towards the end of the episode here. Maybe we could go on for hours talking about this, but we always have the same couple of questions at the very end. One is, if you weren't doing Atmos, but given your sort of space background and aerospace knowledge, is there something else you find very interesting in the commercial space sector right now? And I mean, in terms of like, business model activity, not specific companies.
Yeah, this is something that we are discussing also with my 3 co-founders from time to time. Marta comes from the launch industry, so why not do launches? Chris comes from the German Space Agency, so he's been doing an asteroid mission to Ryugu, mascot Hayabusa 2. So asteroid mining is also quite interesting. But one of the topics that I've been discussing with Jeff, who comes from Airbus Defense and Space quite a lot, is the topic of cloud infrastructure in space, right? So, I mean, it makes perfect sense because we have all of those satellite constellations out there now, most prominently, of course, Starlink, but then also, Kuiper, OneWeb, and also smaller constellations. So connectivity in space is already there. Why not put the data centers there as well? Right? So, I mean, you have unlimited solar power up there. You have unlimited possibilities to get rid of all of the heat by radiators. And you have like the shortest connection to those internet connections via satellites up there. And then, on the downside with terrestrial data centers, you have all of the problems of, land usage, water usage, the electricity consumption that is skyrocketing. So I think if we were not working on reentry from space, I could definitely see myself working on data centers in space. Well, we'll see. Maybe we can combine it at some point. Yeah.
Well, it's certainly an interesting topic, and as I'm sure you're aware, there's some groups working on that right now. So maybe we should have an episode with one of them at some point soon. Last question, Sebastian, always the same. Science fiction. Do you like science fiction? And if so, what are some of your favorites?
Yeah, I do. I mean, I grew up with Star Trek, and then later with Star Wars. And I think that has definitely influenced me in my career choice. But I have to say that I like hard science fiction, right? Like things that seem achievable. One of my favorite movies from the last couple of years was The Martian. And I think the one thing that really inspired me to go from science fiction to actually pursuing a career in this was when I was 17, Burt Rutan launched the Spaceship One to space in California. And that's when I thought, well, maybe a dream, but it might also become true. And that's how I got into the industry.
It's interesting now. In my mind, I started thinking science fiction myself, and where we started this episode with the sort of like the managing the re-entry and the heat and everything. And I was like, in 2001, how did the aliens get that monolith to go to Earth? And it was like pristine. Like it was like clearly some very advanced material sciences going on. But anyway, Sebastian, that was a pleasure. Thank you so much. Best of luck for Atmos and for your next steps. It was a pleasure talking to you.
Likewise. Talk to you soon.
And that's it for another nominal episode of the Space Business Podcast. And once more, if you enjoyed this episode, please leave us a 5-star rating on your favorite podcast platform, such as Apple or Spotify. You can follow us on Twitter at podcast_space. We're also on LinkedIn under the Space Business Podcast. Lastly, if you have any feedback, including ideas for guests, and that may even include yourself if you have an exciting space story to tell, or interested in becoming a sponsor, or really for any other suggestions, you can drop us an email at spacebusinesspodcast@gmail.com. Thanks so much for listening, and see you for the next episode.